Kinship face synthesis aims to synthesize descendants' faces based on the parents' appearance. This technology has many potential applications, such as kinship verification, finding long-lost children, and multimedia social applications. In this paper, we introduce StyleGene, a new framework for kinship face synthesis. StyleGene allows us to generate a variety of realistic descendant faces by leveraging the visual traits inherited from their parents. One notable advantage is that StyleGene's training process doesn't depend on kinship annotation. During training, we extract individual facial genes for each facial region. In the inference stage, we generate the descendants' genes by simulating the genetic processes of crossover and mutation. We then decode the genes to synthesize their facial images. Learning visual genetic relationships becomes more challenging due to the scarcity of large-scale and high-quality kinship annotation data. In particular, supervised learning methods are susceptible to the risk of overfitting. To tackle these challenges, this paper aims to lessen the need for kinship annotation, enhance the controllability and interpretability of facial genetic regions, increase the diversity of facial traits, and simplify the training process to alleviate the training burden. The main contributions of our work are: we present a novel kinship face synthesis framework with controllable facial genetic regions. And we propose a novel genetic strategy by simulating the crossover and mutation to generate the region-level facial genes of descendants. Third, we introduce a gene pool into the mutation process to significantly increase the diversity of the kinship face. Here's an overview of our proposed framework, which consists of 5 main modules. We will now provide a detailed presentation of each module. In this paper, we use the pre-trained StyleGene 2 as the generator, and then invert real images into the W+ space of StyleGene 2 by a pre-trained inversion encoder. At the same time, we use DatasetGene to annotate face images to obtain fine-grained mask annotation. During the training stage, we propose an image-based gene encoder that inputs facial masks and RGB images. The encoder generates a spatially decoupled representation for each facial region. Drawing inspiration from the VAE model, we predict the mean and variance of these representations and employ the reparameterization tricks to sample a vector known as RFGs. Subsequently, the gene decoder maps this vector back to the W+ space of StyleGene 2. We aim to directly use the latent from W+ space of StyleGene 2 as input during the inference stage, without relying on facial mask annotations. Therefore, we propose a latent-based gene encoder. The encoder takes the latent as input and produces the same representation as the image-based gene encoder. Thus, the whole training process is straightforward, with only 2 losses, the reconstruction loss and the decoupling loss. We use the mean squared error loss to measure their errors. This is an image-based gene encoder network architecture. Firstly, a shared-weight convolutional network is used to downsample the 512 by 512 RGB image to a resolution of 64 by 64. Then, the resulting feature map is multiplied by the mask of each region and encoded separately using multiple independent small networks to obtain the mean and variance of each region. The values from multiple regions are concatenated together. Finally, the reparameterization trick is applied to obtain the representation of region-level facial genes, RFGs, for each region. This is the architecture of the latent-based gene encoder and gene decoder. Due to the high dimensionality of the vectors involved, the network backbone draws inspiration from Google's MLP mixer design, employing mixer layers. We do not want the mutational traits of synthesized descendants to be random noise without any basis. Therefore, we build a gene pool. Using a latent-based gene encoder, we pre-extracted RFGs from a large-scale facial dataset, and then grouped them based on facial attributes. The genetic representation of the descendants is synthesized through crossover and mutation processes. Given the parents' photos, we first use a latent-based gene encoder to obtain their RFGs, region-level facial genes. The most straightforward approach is to construct the descendants' RFGs by weighting the RFGs of both parents. This process, called crossover, aims to preserve the similar facial regions between the parents. However, the descendants generated using this method lack diversity. The heat map on the right illustrates the similarity between the descendants and the parents, showing that these children resemble their parents too closely. To address this issue, we introduced the mutation process, which incorporates a gene pool as a mutation term. This means that a portion of the descendants' RFGs is inherited from the parents, while another portion is randomly selected from the gene pool based on the parents' racial information. Notably, the gene pool also facilitates control over the attributes of the descendants' age and gender. This is the inference process, which doesn't require facial annotation. Firstly, the inversion encoder maps the image to the W+ space of StyleGene2. Then, the latent-based gene encoder is utilized to extract RFGs from the parents' facial images. The crossover and mutation processes construct the RFGs of the descendants. Finally, the gene decoder maps the RFGs of the descendants back to the W+ space and utilizes a pre-trained StyleGene2 model to synthesize the facial images. We conducted qualitative, quantitative, and user study experiments to evaluate our method on 3 kinship datasets. This is the qualitative experimental comparison results on the FIW, FF database, and TS-Kinface datasets. Our method demonstrates better realism and diversity. We first performed experiments focusing on kinship verification, where we trained a binary classifier on the FF database training set to identify parent-child relationships. Next, we randomly chose 100 families from 3 distinct datasets and employed these comparisons to generate 40 descendants for each family. We calculated the average verification accuracy by comparing the generated children with their parents. Furthermore, we assessed the diversity among the 40 children within each family by utilizing the LPIPS metric for pairwise comparisons. We also conducted a user study where participants were provided with images of parents and asked to rank the generated children produced by different methods based on their resemblance. We also compared the facial ID feature distribution of the descendants generated by these methods with real children. This paper introduces a novel framework for kinship face synthesis and a new genetic strategy. Our experimental results show that our method outperforms existing methods in terms of realism, resemblance to parents, and diversity. Thank you for your attention.